So so Meng got his PhD degree from Institute of Physics, and then did his postdoc with Bob Bergenal, and now he's a professor at San University in Guangzhou, and he had done many different works with Jeff and many other different people, but his most exciting work recently is his discovery of this 80K superconductor, and this is actually a real superconductor instead of this LK99. But so I'll leave the floor to Meng. Yeah, thank you, Meng. Yeah.
Okay, thank you very much. Yeah, I would like to thank Professor Peng Chengdai for this invitation. I'm very glad to share my recent work in La3Ni2O7 oxygen 327 compound. Yeah, I see Jeff and many friends. I didn't see many years. So yeah, it's midnight in Chinese time, but I'm still excited. So today I will introduce the discovery of simulativity near 80 Kelvin in La3Ni2O oxygen under pressure. So Professor Peng Cheng has introduced me briefly, so I wouldn't do that again. So Peng Cheng was my PhD advisor. Yeah. And at UC Berkeley, I also worked with Professor Robert Bergenal. So after that, I moved back to Yat-Sen University in Guangzhou right now. Okay, so here is the outline for my talk. I will briefly introduce the conventional superconductivity. I heard there are also graduate students who will attend the talk. Then I will also introduce unconventional superconductivity, including heavy Fermi superconductors, copper oxide superconductors, and iron-nitride and calcarenide superconductors. The third part of my talk is the discovery of high TC superconductivity in nucleus, including the introduction of nucleus, the superconductivity, this discovery, and some my personal perspectives. In the end is a summary. So the figure I show you here is the data we just measured on a compound La3Ni2O oxygen. So the transition temperature, that is the superconducting transition temperature, superconductivity transition. So the transition temperature is at 83.6 Kelvin. So it's higher than the transition temperature we report in our Nature paper. So while the resistance didn't reach zero below this transition temperature, is because we measured under pressure. There are some technical details. Okay. So superconductivity, this phenomenon was found in 1911 by Honest. So he measured the resistance for mercury. Below I think it's 4.2 Kelvin, the resistance becomes zero. So they define this phenomenon as a superconductivity. So this discovery was awarded the Nobel Prize in 1913. I think that's the most important phenomenon for superconductivity. So another important phenomenon for property for superconductivity is the Meissner effect, discovered in 1933 by Meissner. So that's a diamagnetic property in the superconducting state for a material. So it will repel all the magnetic field in this material. There is another important property for superconductivity is the Johnson effect. I will not introduce here, but due to these very interesting property, there are very important applications for superconductors. Well, to use a superconductor, there are three important parameters. That's a so-called superconducting transition temperature. That's a TC. We will discuss many times in my talk. Another is the critical current and the critical magnetic field. Actually, the three parameters couple together. So, for example, if we apply a magnetic field to a superconductor, the magnetic field will decrease the transition temperature. There are many applications. For example, maybe many people are familiar with the magnetic imaging device. It can also be used to magnetic energy storage system and energy transportation. The simulativity, for example, the Johnson effect, and some it can also be used to sensitive sensitive device for measuring magnetic field, voltage, or currents. Also, the simulating maglev train. Okay, so in my talk, I will not mention the details of the application. I will focus on the, the materials and mechanisms. Okay, there are many conventional superconductors from the discovery of the simulativity in Mercury in 1911. After that, many elements and alloys are found. You can see in this table. I think they are only part of the conventional superconductors. Well, there is a very important limitation for the transition temperature for conventional superconductivity. That's so-called, I think, it's Macmillan limit. It's the 40 Kelvin. That's due to based on the BCS theory proposed in 1957. The electron phonon coupling will limit the maximum transition temperature for conventional superconductivity. I think before 1972, the maximum TC was 23.2 Kelvin in this diomium germanium. Okay, so for the BCS theory, it's proposed by Badin, Cooper, and Schrieffer in 1957. It told us, the electron and phonon coupled together to give this zero resistance for superconductivity. Well, in this theory, there are three important parameters. That's the bifrequency of a material and the electron phonon coupling, the strength of electron phonon coupling. Then the density of states at the Fermi level. For a real material, there are all limitations for the three parameters, but under high pressure, we can get higher the bifrequency and maybe higher density of states and stronger electron phonon coupling. Well, the BCS theory was awarded the Nobel Prize in 1972. Based on this theory, people actually theoretically predict there may be higher, maybe even room temperature superconductivity under extreme high pressure for the cathode hydride materials. I think in recently, maybe from 2015, there are many compounds were discovered. They show superconductivity under extreme high pressure. The transition temperature is very high. It's about 200 Kelvin. Well, but the mechanism is clear. It's a BCS. Under high pressure, the vibration of atomic hydrogen can promote the TC. So actually, in our research work, we also use this diamond IV cell technique to apply pressure on our sample. But the pressure is much lower than the cathode hydride materials. Okay, So I will move to the unconventional superconductors. So for unconventional superconductors, that means unconventional means the mechanism of superconductivity could not be understood by the BCI theory. There are not a theory for unconventional superconductivity. Heavy Fermi superconductors, copper oxide superconductors, and iron nitride or iron tacrylide are three main systems of unconventional superconductors. Okay, the first one is the heavy Fermi superconductors. It was discovered in 1979. I think I can use the laser. In 1979 by Staglish. You can see here is the strong cerium copper silicon 122 compound. The transition temperature is very low. It's below 1 Kelvin. Okay. But for some compounds, by doping or pressure, the transition temperature can be improved a little bit, but it's still low. Well, but even the transition temperature is low, but it's still higher than the expectation of electron phonon coupling by the BCS theory. So the effective mass of electrons for heavy Fermi superconductors are 1,000 times of the bare electron mass. So I think that's the origin of this name. Okay. The second system of unconventional superconductors is the copper oxide. That's the most, I think, maybe the most important systems. The TC above the boiling point of nitrogen at 77 Kelvin. That is also called the high TC superconductors. The high TC superconductor, the copper oxide, was discovered by Bernard and Mueller in 1986. So you can see here that's the barium doped lanthanum copper oxygen. That's could be 113 compound. Okay, the transition temperature is at 35 Kelvin. But soon after the discovery of the superconductivity in copper oxides, the transition temperature was improved above 77 Kelvin. This is the yttrium barium copper oxide. The transition temperature is 93 Kelvin. The key structure for this copper oxide is a copper oxide layer. That's a quasi two-dimensional material. So there were many systems of cuprates were discovered later on. So currently the maximum TC for cuprates is 100, I think it's 135 Kelvin at ambient pressure. Under pressure, it is 165 Kelvin. In 2008, Professor Hosono discovered superconductivity in iron-based superconductors. That's a phosphorus-doped lanthanum iron arsenic oxygen. That's a so-called 1111 system. So the transition temperature is at 26 Kelvin. By replace lanthanum by strontium, it's a SM, this compound, this element, the transition temperature could be improved above 40 Kelvin. It's the TC is 43 Kelvin in this compound. So it exceeds the Macmillan limit. That means this is also an unconventional superconductor. So after that, several other iron-based superconductors were discovered. Well, here's many compounds of iron-based superconductors discovered from 2008 to 2012 by physicists from many countries. But the superconducting transition temperature all below the boiling point of nitrogen at 77 Kelvin. There are some study for the single layer iron selenium. I think from spectroscopy measurement, they suggest that the transition temperature may be above this, maybe above 77 Kelvin. But I think there were not resistance and magnetic susceptibility measurement to confirm that. Okay, so how to understand the mechanism of unconventional superconductivity? So we need to so people studied the structure, the magnetic structure for these materials. If we look at the phase diagram for heavy fermi superconductors, copper oxide superconductors, and the iron-based superconductors, the superconducting region all near with the antiferromagnetic order. Okay, so so we call the parent compound. Okay, the antiferromagnetic order state is a parent compound of superconductivity. So for for a compound with the long-range magnetic order, there must be magnetic correlations. We can use the inelastic neutron scattering technique to measure the magnetic correlation. That's the spin wave. Right? By fitting the spin wave dispersion to this Hamiltonian, we can get the magnetic exchange interactions. So these properties are thought to be universal for all the unconventional superconductors. So what interesting is even by doping or the other tuning parameter, we can suppress the long-range magnetic order, but the magnetic excitations the magnetic excitations are very robust. That means even in the superconducting state, after we doped carriers to the parent compound, the long-range magnetic order have been broken. The magnetic fluctuation or magnetic excitations are still there. So another evidence, for the intimate relationship between magnetism and the superconductivity is the so-called spin resonance. Spin resonance can be measured directly by inelastic neutron scattering. So in this uranium tellurium-2, that's a heavy Fermi superconductor. The transition temperature, I think it's very low. It's below 2 Kelvin. Okay, that's 1.6 Kelvin. We can measure the inelastic the spin excitation spectrum here in this figure. This is energy. This is Q. We can see. I think this spot is the spin excitation. If we measure the spin excitation at the temperature below the superconducting transition temperature, we can see the enhancement of the spin excitation. Okay, compared with the normal state. Okay, this is measured in iron-based superconductor. That's a potassium-doped barium 122 system. Okay, we can see below the superconducting transition temperature, there's a strong excitation spot here, but above the transition temperature, the intensity decreases. We can define the energy of the spin resonance. So if we summarize all the energy of the spin resonance in cuprates, iron-based superconductors, I think even including this heavy Fermi superconductors, the energy of the spin resonance is proportional to the superconducting transition temperature. That's another evidence, for for this spin fluctuation mediated co-pairs for unconventional superconductors. Here are some other examples for spin resonance in heavy Fermi superconductors and cuprates and ion-based superconductors. You know, the spin resonance is very clear. So here are some conclusion people have got from the study in the other systems. The neutron spin resonance follows the order parameter of simulativity. That means if we measure the temperature dependence of the spin resonance, we can see a clear kink at the simulative transition temperature. Okay, the low energy excitation and the spin resonance are dominated by Fermi surface nesting. The energy of spin resonance is proportional to Tc, and the existence of spin resonance supports spin fluctuation mediated co-pairs. Okay, in addition to the long-range magnetic order and the spin resonance or spin fluctuations in the superconducting compound, there are some other competing orders we can see in these phase diagrams. For example, let's take this one. For example, there is pseudo gap region and the charge order and the strange metal region, and here is the spin density wave. So we want to know what are the important parameters for high temperature superconductivity or unconventional superconductivity. So if we look at the three unconventional systems, you know, they share many similarities in the phase diagram. But so far, as I said, there isn't a theory to understand the superconductivity for these compounds. So we need to we need to explore superconductivity in the other systems. Okay, here is the transition temperature for different systems as a function of time. You know, cuprates is the only system which superconducting transition above the nitrogen boiling point. We want to know are antiferromagnetic fluctuation universal for unconventional superconductors, and are there the other high TC superconducting systems? So actually, people have invested lots of efforts to explore superconductivity in the other transition metal compounds. For example, chromium, manganese, cobalt, and nickel. I think recently people also discovered superconductivity in this vanadium compound. Even the materials I list here are all superconductors, which show superconductivity at ambient pressure or under pressure. For some compounds, for example, chromium arsenic, this is manganese phosphorus. They all show very interesting phase diagrams, which are similar with the cuprates and the iron oxide superconductors. Here is the water intercalated sodium, cobalt, oxygen. It also shows very interesting compound with charge ordered insulator state and magnetic ordered state. But the problem for these materials, the transition temperature are all very low. I think maybe all below 5 Kelvin. The mechanism for some compounds is BCS, is electron phonon coupling. No high TC superconductivity was found for these compounds. Okay, so let's focus on this nucleus. Okay. So here's the spin configuration for copper with 2+ valence state. It has 9 electrons on this 3D orbitals. Well, nickel is near with copper in this table, right? So if for nickel with the 1+ valence state, it has the same spin configuration with copper 2+. Okay, so the spin configuration for copper 2+ and the nickel 1+ is identical. That means well, theoretical physicists have predicted there may be superconductivity in nucleus with a nickel 1+ valence state. So the history for the study of nucleus was very long. This figure is from a review paper. So in 1983, the lanthanum nickel oxygen 2, the 1,2,2 compound had been was synthesized. And after that, the cuprates, the superconductors, was discovered. Then later on, the other systems of nucleus were discovered, including this is the 438 compound in 1992, and the 113 compound in I think the single crystals for 113 compound was synthesized. Okay, that's single crystal. The synthesis of the 113 compounds were very early. I think it's in 1950s. Okay, here 326 compound was synthesized in 2006. Well, I think there were many studies between 2016 and 2020, because I think a group in Argonne National Lab, they could be able to synthesize single crystals of the nucleus. That's very important progress, for the study of this material. People want to get a superconductivity in nucleus as a theoretical theories predict, but until 2019, a group at Stanford, that's Howard Huang's group, they discovered the superconductivity in strontium doped neodymium nickel oxygen 1,2,2 thin films. Okay, I will show you later here. Okay, so they grow the strontium doped 113 compound. Okay, film. Then they use this so-called topochemical method to remove the apical oxygen of the octahedral and get this infinite layer phase. Okay, so you can see here the apical oxygen have been removed. On this film, they observe superconductivity with a transition temperature at around 9 to 15 Kelvin. Okay, we can see here by applying pressure, the superconductivity is suppressed. This the superconductivity in these systems have been confirmed by many groups of the world. The valence state for nickel in this compound is 1.2 plus. Okay, 1.2. It's similar with copper in cuprates. Okay, so but superconductivity only appears in films. The TC for, well, here is the isostructure cuprates. That's also 112 compound, calcium doped strontium, copper oxide 112 compound. But for cuprates, for the isostructure cuprates, the transition temperature is at around 110 Kelvin. It's very high. Well, here is the spin citation of the 112 nucleus measured by Riggs, because it's a thin film. We can see the spin excitations. The top of the spin excitation is around 200 MeV, million electron volts. So it's comparable with cuprates. So that means the magnetism, okay, in this nucleus, the 122, the 112 system is similar to that of cuprates. That means maybe, okay, if we think the spin fluctuation is important in the mechanism of nucleus, okay, in this compound, that means the mechanism may be the same for the 112 system to cuprates. Right? Okay, here are different systems of nucleus. Okay, this is the so-called infinite layer. This is a single layer, bilayer, and trilayer. The number of, the number of N means the number of nickel oxygen layers in a unit cell. For example, this is a 327 compound. There are the bilayer of nickel oxygen in a unit cell. So we call these systems with nickel oxygen 6, the octahedral. We call this system is the RP phase. Okay, after remove the apical oxygen, it's the reduced RP phase. Okay, so the superconductivity was discovered in this compound or in this structure. Strontium doped 112 compound. In different materials, the nickel has different valence state. For example, in this 327 compound, nickel, the average valence state for nickel is 2.5. But after we remove oxygen, the valence state is 1.5. Okay. For this 4310 compound, it's the valence state for nickel is 2.67. After removing apical oxygen, the valence state is 1.33. Okay, the most stable state for nickel is 2+. Okay, so when we grow single crystals, it's very easy to get this 214 phase. But if we want to grow the other systems, that means 214 phase is a pure, it's a impurity, and it's very difficult to get rid of. Okay, here's the phase diagram for nucleus with different 3D electron counts. Okay, you can see the axis. Here is the 7 electron counts. That's for the 113 compounds. In these compounds, the nickel has the valence state for nickel is 3. Okay, this one is 4310. This one is 327, and this is 214. Okay. Here's 326, 438, and 112. Okay. The superconductivity was discovered here. Okay, where the valence state for nickel is 1.2. Okay, it's also comparable with the cuprates. Okay, this is the phase diagram for cuprates. So the superconductivity was discovered in films. We want to get a superconductivity in bulk materials. So I think many people tried to get superconductivity, in the compounds near this region, in 436, 438, or 326 compounds, maybe under pressure or the other, or by doping. That was also our motivation to study these materials. But if we want to study 326 compound, we need to grow single crystals or powders for this 3 to 7. Then we use this chemical method to remove apical oxygen to get 3 to 6 compound. Okay, that's the reason we have to grow single crystals of 3 to 7 to study this compound. Actually, there were many studies on 3 to 8. Sorry, it's 4, 3, 8 and 4, 3, 10 compound. Many studies were conducted by Argonne National Lab. So that's why we chose this bilayer system. Here is a comparison with the mercury cuprate superconductors. That's also a single layer, bilayer, and a trilayer compound of cuprates. But for this material, it has very high TC. The transition temperatures are about 100 Kelvin. Okay, so before our work, I think no studies on lanthanum nickel oxygen 3 to 7 compound for single crystals. Okay, the powders were synthesized quite early. Okay, here's the timeline of the superconductivity study. Okay, here I will introduce the study on this 3 to 7 compound. Okay, this material was synthesized in I think early 1980s, maybe in 1981. But they have known there are weaknesses for oxygen. Okay, after the discovery of cuprates, people I think paid more attention to this system. Many studies were conducted at 1990s and 2000, including the transport, magnetic, and the thermal properties, neutron diffraction, and the NMR measurement. There are also band structure calculations conducted before 2000. Okay. So people have known, so it's very easy to get integrals of the 3 to 7 compound and 4, 3, 10 compound during the sample synthesis. Actually, even there were high pressure measurements on this compound, but they didn't observe superconductivity. I think that is because the deficiency of oxygen in that sample. I will discuss the details later. Okay, so we got single crystals, and by applying pressure, we found the superconductivity on our single crystals. We have 2 related papers published recently. Okay, when we plan to grow single crystal, we found actually it's very difficult because the valence state, okay, the most stable valence state for nickel is 2. So the stable phase is 2 and 4. Okay, if we want to grow the other systems, we need to apply oxygen pressure. We need, okay, so the pressure window for 3 to 7 compound is very narrow, as you can see here. Okay, it's only several bar. Okay, if we apply higher pressure, we will get this 4, 3, 10 compound. Okay, here is 113. It's easier than the 2 compounds. Okay. One of my PhD students, he used more than 2 years to grow this single crystal, and finally he succeeded in getting pure phase single crystal for 3 to 7 compound. Okay, here's a picture of this single crystal. Okay, this is a law diffraction measurement. Well, if people familiar with cuprates, the whole single crystal could be with the same orientation, but for nucleus, well, based on our experience, there are millimeter-sized single crystals if we crash this big single crystal. But they all have different orientation. This may be related to the structure. This is an orthorhombic structure where A and B is not equal. That means there will be many the twinning effect will affect the quality of the single crystal. Okay, here's the calibration of the single crystal at ambient pressure. This is a resistance measurement. Well, in resistance measurement, we can see actually there are two kinks, one at 153 Kelvin, another is at 110 Kelvin. Okay, so the kink at 115.3 Kelvin is difficult to be observed because the resistance is very low for this material. It's very metallic. So, but if we polish, the single crystal to be very thin, in our case it's 80 micrometers. So to enlarge the resistance, we can observe this kink. Okay. We can also see a kink on a magnetization measurement and a heat capacity measurement. Okay, so based on these observations, we thought there may be a charge density wave transition in this material. That was also predicted by some theoretical paper. We also analyzed the valence state of nickel in this compound. Here is the XPS measurements. The conclusion was there are mixed valence states of nickel 3+ and nickel 2+. Okay, so as I said, our motivation was to get bulk superconductivity in 326 compound. So we applied pressure on that compound, but we didn't observe superconductivity. Okay, so now I will move to the introduction of the superconductivity in this compound. Here is the resistance we measured under pressure. Okay, this one is was measured at ambient pressure. It's very metallic. Okay, but after applying pressure with the diamond IV cell technique, we see weak insulating state. The resistance goes up at low temperatures. By increasing pressure, we can decrease the resistance. Above 14 gigapascals, we see a sharp. It's not very sharp. We see a drop on resistance at 80 Kelvin. Well, if we only see this drop, the drop could be originated from maybe CDW or SDW. So but it can also be a superconducting transition. So we changed it to we repeated the measurements many times. So later on, we replaced the pressure transmitting medium to potassium bromine. So this is a softer material, so we can get a more homogeneous pressure. Okay, with this diamond IV cell. So here is the resistance. Well, when we got this data, we are very confident this is a superconducting transition, because you can see here the linear resistance, right? That's a so-called string metal state in the normal state, okay, for the unconventional superconductivity. Right? And then this is a sharp transition. Here we see a flat stage Well, we if you see here, the resistance didn't reach zero. Actually, that's very common for high pressure measurement. I will show another example to you later. To demonstrate this is a superconducting transition. We need to apply pressure. We need to apply magnetic field to suppress the superconductivity. Well, here's the resistance measurement under magnetic field. We can see the suppression of superconductivity, right, under pressure. We can fit the upper critical field by Ginzburg-Landau formula. The upper critical field is around 100 Tesla to 200 Tesla for the samples at different pressure, because at different pressure they show different transition temperatures. We also need to measure the diamagnetic property for the superconducting transition, but actually it is very difficult to measure diamagnetic susceptibility at this pressure. So we use the technique, so-called mutual inductive magnetic susceptibility measurement. Okay. Actually, this is the raw data. Okay, it's close to a linear, but there's a drop at the transition temperature. We just subtract a linear background, we can get this susceptibility, this magnetic susceptibility. Okay, so that's the diamagnetic response of the superconducting transition. Okay, so we have demonstrated the transition from resistance measurement and magnetization measurement. Okay, here's the example I will show you on the measurement of barium iron 2 sulfur 3 compound. That's a spin ladder compound. Okay, here's the resistance with this diamond IV cell and sodium chlorine as a transmitting as a pressure transmitting medium. So you can see here the drop. Okay, the superconducting transition is the drop is very small. Okay, at this pressure. But if we change the pressure transmitting medium to glycerine, that's a liquid pressure transmitting medium with the cubic IV cell technique, we can see very good superconducting transition. We can see the resistance has achieved zero, right? So that means if we compare our data, okay, that means you can see the transition temperature, the superconducting transition actually is very good. Okay, so we repeated our measurements on many samples. Here you can see the on-site transition temperature is at 80 Kelvin. Okay. Here are the resistance measured under magnetic field. Okay, here are the diamagnetic susceptibility measurement under pressure. They are the raw data. We can see the transition. If we decrease the pressure, for example, we measure this signal at 4.3 gigapascals. It's just a linear. We couldn't observe the kink. So that means this anomaly was due to the superconducting transition. Okay, I will show you the structure under pressure. We have calibrated the property of the material at ambient pressure. Okay, this is the synchrotron X-ray diffraction measured under pressure at room temperature. If we only see the diffraction peaks, maybe there isn't there were not new Bragg peaks. Okay, but if we analyze the diffraction very carefully, here is the peak position. Okay, as the position of the peak Bragg peak as a function of pressure, we can see there's a stage here, maybe between 10 and 20 gigapascal. That may indicate a structure transition. Okay. Here's the pressure dependence of the lattice constant. We can also see this this stage. Okay. Okay, here's the volume of the material and the pressure. So as you know, X-ray is not very sensitive to oxygen. So actually, it's we could not be able to determine the structure and the pressure very accurately. But we can analyze the structure, you know, based on many studies previously. We can also combine with theoretical analysis. I will show later this slides. Okay, here's the diffraction data we refined. Use the EMM structure at ambient pressure and the FMM structure for under pressure. Okay, see they fit the refinement fit the data very well. Okay, the conclusion is that if we combine the theoretical analysis and our experimental data, we determine the transition is from EMM to FMM. The difference for the two structures are the angle between the nickel, oxygen nickel, from 168 degree to 180 degree. Okay. Okay, here are some details of the structure. Okay, if we summarize all our data on this phase diagram, okay, we can see there's a structure transition here. After the structure transition, we observe superconductivity. The onset of the superconductivity is at around 80 Kelvin. It's very high, about the boiling point of liquid nitrogen. By increasing pressure, the transition temperature is suppressed a little bit. Okay, but actually here is also if we actually for here is also superconducting transition, but for the pressure here, we can only see a drop on resistance, so we didn't plot a point here in this area. And you can also see the color on this area is very homogeneous. Okay, that means the it's a linear resistance. It's a strange metal area. Okay, another feature in this phase diagram is the weakly insulating state here. As you know, at ambient pressure, the material is metallic, but after applying a very small pressure, it will become a weak insulator. This is hard. This phenomenon is difficult to understand. Okay, so after the measurement, we collaborate with the other people in this with this cubic MV cell. We know right now actually this weakly insulating state is not intrinsic. It's caused by the diamond MV cell technique. Okay, I will show you later. Because we didn't observe zero resistance, so we collaborated with many other groups to measure the resistance. This is conducted by Professor Jin Guangcheng's group in IOP in China. Okay, they also use the diamond MV cell technique to measure the resistance and the pressure. The data are consistent with our results. That's the weakly insulating state. this is a superconducting transition. But if we use cubic MV cell, okay, with I think with this technique, we can see they are all metallic, even for the pressures below the superconducting transition pressure. Okay, so that means the metallic state is the intrinsic property for this material under low pressure. In this measurement, they observe zero resistance. Okay, here's the zero resistance below, I think, below 10 Kelvin. The reason for I claim the superconducting transition temperature is at 80 Kelvin, but here the zero resistance only show below 10 Kelvin. That's because, okay, the transition actually is above 15 gigapascal. Okay, but the cubic MV cell, the maximum pressure for cubic MV cell is 15 Kelvin. 15 gigapascal. So at this pressure, the superconductivity is not very good. Okay. So we also collaborate with Professor Huiqiu Yuan's group in Zhejiang University. They measure the resistance use the diamond MV cell, but with liquid transmitting pressure medium. Okay, so the data are very good. We observe zero resistance, okay, and a linear resistance about in the normal state. Okay, so we can also observe the pressure dependence of the transition temperature. Okay, here is the phase diagram we plot. This one is a CDW, but actually I need to clarify there isn't directly experimental observation for CDW. Okay, so yeah. Okay, so now we have demonstrated this is a superconducting transition, but how to understand the mechanism? So at least we need to know the electronic structure, right? We did the DFT calculations. Okay, at ambient pressure or low pressure, this is calculated for 1.6 gigapascal. Well, the nickel, the density states of nickel dominate the electronic structure on Fermi surface. The 3D x square minus y square across this Fermi level. Okay, that's this one. The 3D z square, dz square below the Fermi level, there's a gap here. You can see a gap here. That's a so-called sigma band. Okay, sigma band. It's below the Fermi level, but under pressure, after the structure transition, this sigma band touch the Fermi level. Okay, the gap is closed. That's a so-called sigma band metallization. Okay, we think the appearance of superconductivity coincidence with the metallization of sigma band. Okay, that's this the metallization of the sigma band is very important for superconductivity in this material. So if we think about the spin configuration for nickel in this for this bilayer systems, we need to think about two nickel ions. So we think here is a spin configuration, for in this system. Along the c-axis, okay, along the c-axis, there's a bonding and anti-bonding state. That will split the 3dz square orbital. Okay, so two electrons from the bilayer nickels will occupy the lower 3dz square state. Okay, so that means that actually that's the origin of a strong electronic correlation. Okay, But for this 3D x square minus y square orbital, there is only one electron occupy this energy. That's the one quarter occupation. That means the correlation would be weak for this 3dx square minus y square electrons. Okay, that's the intralayer correlation. And for the 3dz square, that's the interlayer correlation. Okay, so well, there are many theoretical analyses after our work, so I will not introduce too much. But I have opportunity to discuss with many theoretical physicists. So I think the two nucleus, this one from bilayers, they form a singulate. Okay, they form a singulate. But without pressure, it's below the Fermi level. By applying pressure, it will touch the Fermi level, and it's kind of hole doping. Then the 3D x square minus y square electrons will hop to this orbital, and it can mediate the electrons and form this group pair. That's a very simple understanding from the discussion with the others. Okay, so our collaborator, Wen's group, they studied the electronic correlation and the energy gap of the density wave-like transition at ambient pressure with optical technique. Okay, they found I think there are several important conclusions. One conclusion is they determine the energy gap of the charge density wave-like transition is at 50 milli-electron volts. Okay, and the strength, okay, the strength of the correlation of the electronic correlation is here. Is very strong. It's comparable with the cuprates. Okay. Okay, here many people are interested with are curious about the spin excitation in this material. Here is our inelastic neutron scattering measurement on this sample, on a powder sample. It's unpublished data. We collected on Merlin at ICES in UK. Okay, so actually we didn't see any magnetic excitation. Okay, as you can see here, measured at 7 Kelvin with different incident energies. We didn't see spin excitations. You can see here are the data at collected at 300 Kelvin. We can see some excitations. Actually, they are phonons. This is stronger at 300 Kelvin. But I need to clarify. The samples are powder samples we synthesized at ambient oxygen pressure. That means, okay, there must be some oxygen vacancies on this compound. Okay, so we couldn't exclude. We couldn't exclude the possibility for spin excitation existing in the superconducting state under pressure. Okay, so because many theories are based on the Fermi surface netting picture, they predict that there will be spin resonance or spin fluctuations for the superconducting state. But here's our experimental data measured at ambient pressure. Okay, this is for ambient pressure. We couldn't do high pressure measurement. Inelastic. We couldn't do high pressure inelastic neutron scattering measurement currently. Okay, so actually the main part of my talk is almost done. Here are the recent research progress on this compound. There are many theoretical papers Okay, and also highlight written by Danfeng Li in Hong Kong City University. Actually, we are collaborating with more than 30 researchers all over the world, including some researchers in the US with different techniques to study the physicists in this compound. Okay. I think I have used all my time, right?
Yeah, yes. Okay.
Okay, so here are some previous studies on this material. Here I will show, just briefly show you oxygen will increase the resistance, okay? It will change the metallic ground state to insulating. That's why we think our sample, in our sample, the oxygen is very close to 7, okay? Because it's very difficult to accurately determine the oxygen content. Okay, here are some high pressure measurement on this sample in previously to our measurements, even at 18.5 gigapascal is still insulator or insulating state. That's because for their sample there must be some oxygen vacancy. Okay. Okay, here's my perspectives. It's possible, I think it's possible to get high TC superconducting samples by annealing the sample in high pressure oxygen. Okay, it's also possible to get high TC superconducting samples at ambient pressure. We are working on that by doping or annealing. Magnetic order and spin fluctuations are different from that of cuprates. Okay, here's also some previous study. Okay, here's my summary. We found a nucleate with high TC superconductivity at 84 Kelvin right now. The samples are not homogeneous. The content of oxygen is crucial for superconductivity. Okay, so I think by compare nucleates, cuprates, and iron-based superconductors, we may be able to find the key ingredients for high TC superconductivity and to finally solve the mechanism. Here is our collaborators at Yat-Sen University, at Tsinghua University, and some other institutions. Okay, so I will finish my talk. Thank you for your attention.
Yeah, thank you, Meng. Yeah, for very nice pathological talk. Yeah. Okay, so the talk is open for question. Let me ask the first question. So I mean, you said what is the transition at 100K? You said the higher transition may be CDW, but what is the transition at 100K?
Well, this is a very important question. Actually, we don't know the answer right now. If you look at here, it is optical measurement. Our collaborator claim there's a transition at around 112 Kelvin. So I don't know. We only observe this weak transition here. We are working hard to observe to look for CDW by X-ray scattering technique, but we didn't see it right now. Yeah.
Okay, Qimiao.
Yeah, nice talk. So on these magnetic excitations,
yeah,
I wonder whether one could try to look for higher end.
I didn't show the data here, but actually we have
maybe maybe at the energies you're measuring, 24 MeV and below, it's sort of in the suppressed.
Actually, we have more data. I didn't show them here. We have measured the excitation up to 160. We didn't see magnetic excitations.
Why don't you do single crystal, Meng? I mean, you said you did on powder samples.
As you know, so the big single crystal is the orientation is they don't have the same orientation. Okay, so it's kind of powders for inelastic neutron scattering measurements.
I see. No, I mean it's clever to do inelastic do powder first, try to see whether there are any excitations. But I mean, I'm surprised. I mean, actually, can you use optical ways to determine the valence of nickel to know whether there's actually a moment on nickel?
We are working on that. We have some data, but we didn't finish the analysis.
Okay. I mean,
at ambient pressure, the FPS suggests it's a mixed valence state for 2+ and 3+. But under pressure, it's well, we are working on that, but it's not easy.
Okay, JP, yeah.
Hi, yes, very nice work. Just a quick question about the samples. Do you have to dig out these crystals out of the floating zone pool, or is that whole rod the same phase?
Actually, it's a very good question. We grow the single crystal with a floating zone technique. Okay, the single crystal is very big, but it's not homogeneous. If we are lucky, we can get a big, very big single crystal with the single phase. But sometimes there are the other phase. For example, 214 phase or 4310 phase. So we need to calibrate the single crystal very carefully. We need to do the structure analysis and resistance, susceptibility measurement at ambient pressure to determine the phase.
Okay, thank you.
Yeah, Kazu. Oh, the Chandra has a question. Meng, let's get Kazu to ask, and then I'll read Chandra's question.
Yeah, thank you very much for a very nice talk. Actually, I'm very excited about your discovery because in a 2017 paper, we actually proposed that this very material can be a very good candidate for high DC superconductivity due to the interlayer coupling. So my question is, you mentioned that this oxygen deficiency is important for superconductivity, whether there is an oxygen deficiency. So you're saying that you need single crystals to get rid of this oxygen deficiency. So my question is, for example, if you can get rid of this oxygen deficiency in powder samples, you expect superconductivity as well?
Yeah, that's a very good question. I think your theoretical paper was published on PRB, right? So
yes.
Yeah. I know that paper. We we have cited that paper in our in many our papers later on. So but I didn't notice that one this work. Okay, so I will answer your question. Why we think oxygen deficiency is very crucial for the superconductivity here. Actually, we measured many samples of this compound. If there's the oxygen vacancy, we can see the difference at ambient pressure from resistance and susceptibility. For those materials, by applying a pressure, we couldn't tune superconductivity. Okay, so actually we can. It's possible to get superconductivity on powder samples if we can get rid of the oxygen vacancy. We use single crystal because we need to grow the sample under oxygen pressure. So we grow the single crystal. Use the floating zone furnace. Our floating zone furnace can apply oxygen pressure. If somebody can, as I said here, it's possible to get high TC superconducting samples by annealing powder samples in high pressure oxygen. It's possible. As I know, actually, some group have achieved superconducting powder samples by this technique. Okay.
Thank you.
So let me try to ask for Chandra Verma. So he basically asked the question among that, can you show susceptibility data, for let me read his question again. I guess what was Chandra's question?
Yeah, here's
Would you please show susceptibility data as a function of temperature in superconducting compound, as well as non-superconducting compound at ordinary pressure? I guess he wants to know zero pressure. Yeah, zero pressure susceptibility data. Oh, that's it, right?
Yeah. This is measured at ambient pressure. For a sample which show superconductivity under pressure. Actually, this is a very important question. We can, if you see here, about this temperature, the susceptibility, increase as we increase temperature. But if there are oxygen vacancies, the susceptibility at low temperature is very strong, and the property or the phenomenon here maybe maybe we couldn't see this phenomenon. Okay.
I see.
I can also show you another data here. I think this one. This were conducted many years ago for different compounds with different oxygen content. This is for this compound has lots of oxygen vacancy. This is a magnetic stability.
So what's the reason for the dramatic rise below 100K?
What I find remarkable is that the second figure shows a magnetic susceptibility which is 2 orders of magnitude larger than the figure on the top.
You mean
2 times 10 to the minus 3, and this is 2 times 10 to the minus 1.
Okay, yeah. Actually,
so in other words, it appears that if you reduce oxygen, the compound is almost magnetic. This is the gigantic susceptibility. What you're looking at the bottom.
Right.
Even 2 times 10 to the minus 3, which you are seeing on the top, is a very large paramagnetic susceptibility. It's not quite like heavy fermion, but it's almost there.
So what is the reason, Meng, for this rapid rise below 100K? I mean, I'm very puzzled.
Well, here they have given an interpretation. It's electrons localized at oxygen vacancies dominates the susceptibility at low temperature.
Okay, that's pretty nice interpretation.
Yeah.
Okay. Lu Li, and then Dan, yeah.
Oh, beautiful work. So I guess I would say that Chandra raised a great question. I assume that this is another evidence of mixed valence. My question is more about your superconducting states. So what happens? So in the AC stability, in the mutual inductance measurement, what happens to all phase? 90 degree away. Do you see a peak there?
You mean 90 degree?
Yeah. So this is Chi1, right? Usually people plot Chi2. So the 90 degree is in your mutual inductance data.
I didn't show the data in that temperature range. It's if you see the data in a small range, it's linear. We didn't see any anomaly at 90 Kelvin. But if you see all the data in a very large temperature scale, it's kind of the the quadratic feature, something like that. Yeah.
Interesting. I see.
Yeah.
Okay. Thanks. Yep.
Yeah, Dan.
Yeah. Really beautiful. I wanted to ask you. You mentioned these are orthorhombic. A is not equal to B.
Yes.
I'm wondering how much is the difference, and do you have anisotropy in the resistance and things like that? I'm not sure I saw that in.
Yeah, here. Here is the A of 5.43 of this is 5.37.
Okay, it's quite noticeable. How about resistivity or
it's
other?
Twined. The sample is twined. difficult.
Yeah. We
Not
couldn't
possible.
detwin
Couldn't
the sample. We couldn't detwin the sample.
Okay, yeah, thank you.
Okay, yeah, yes, yeah, thank you very much. Yeah. I mean, any other question? Okay, yeah. Yeah, thank you, Meng. Yeah, for getting up so early. We exhausted
Thank you
all
much
the time though.
for giving me
Yeah,
this opportunity.
Yeah, thank you. Yeah, Lou, can you call? Yeah, okay. Okay, thank you guys. Yeah. Thank you for attending this.